Welcome to lecture number 23 for ECE 211 Circuits 1. In this lecture, we're going to talk about phasors. Now, phasors are a way to represent sinusoidal voltages as well as the impedance of resistors, inductors, capacitors. The basis of phasors is sine waves. So up until now, we've been dealing with DC signals. Now, from this point onward, throughout the entire curriculum pretty much, we're going to switch from DC to AC. What a sine wave looks like is this. So here's an RC circuit. This is described by a differential equation. But just look at the input and run it. That's a sine wave. It goes up and down, up and down. Sine waves are all about the unit circle. Well, sine waves are unique. Sine waves are eigenfunctions. What that means is if I have a differential equation, for example, this circuit is described by a first-order differential equation, and run it, if the input's a sine wave, the output, the orange line, is also a sine wave. Now, sine waves are the only function that does that. Sine waves are eigenfunctions. If I change the input, let's make it a triangle wave. If the input is a triangle waves are not eigenfunctions. Input's a triangle wave, output is no longer a triangle wave. If the input is, let's try sawtooth wave. Input's a sawtooth wave, the blue line. Output is no longer a sawtooth wave. So relating the input and the output is kind of complicated. To do that, you need a differential equation. If I try a square wave and simulate it, input's a square wave, output's no longer a square wave. So relating the input and the output is complicated. I need a differential equation to do that. Well, sine waves are eigenfunctions. With a sine wave, if the input is a sine wave, the output is a sine wave. Sine wave in, sine wave out. The difference is change in amplitude and a phase shift. That's where polar or complex numbers come into play. I can represent that with complex numbers. I have an amplitude and an angle. That's polar form. I've also output a sine wave, meaning it has sine and cosine terms. That's rectangular form. So when you're dealing with sine waves, it's much simpler. All I need to describe the output are two numbers, amplitude and delay, or sine and cosine. So describing circuits with sinusoidal inputs is much simpler than other inputs because sine waves are eigenfunctions. To describe a sine wave, I just need two numbers, the amplitude and delay, or sine and cosine. Those are complex numbers, that's phasors. And it's not really that limiting. It's only limited to sine waves, but with a thing called Fourier transforms, a future topic, I can represent any periodic signal with sine waves. So what we're going to talk about here are phasors. What phasors are, how to represent voltages using phasors, how to represent resistors, inductors, capacitors using phasors, AC circuit analysis using phasors, and the HP42 calculator. In my opinion, the best calculator ever built for electrical computer engineers. It handles complex numbers and phasors with a breeze. So starting out, the first half of the course, we looked at DC analysis. With DC, you can represent voltages with a real number. I can represent currents with a real number. I can represent resistance with a real number. We're now going to switch over to AC. From this point onward, everything's AC. Pretty much everything in the ECE curriculum will go to AC. There's only so much you can do with DC. But now that we're using sine waves, I need two terms, sine and cosine, or amplitude and angle. That'll be complex numbers. When I include inductors and capacitors and capacitors are different than resistors. Inductors differentiate current, capacitors integrate current. I'll need to come up with a way to represent the impedance of a capacitor and inductor using phasors. And finally, we'll look at using complex numbers to analyze an AC circuit. That's phasor analysis. So, starting out, as a review of last lecture, if you have a complex number, it has two terms. It has a real part and a complex part. I can also express it in polar form as an amplitude and an angle. And you can convert from one to the other back and forth. Two different ways of representing a complex number. For a voltage, Euler's identity says that e to the j theta is cosine omega t plus j sine omega t. So if you look at the complex plane, if this is j, complex side, this is real. Take the unit vector and spin it, going around the unit circle. The real part starts at 1, goes to -1, +1, -1. The real part is cosine. The complex part starts at 0, goes to 1, 0, -1, and so on. The complex part is sine. Put the two together, I have a vector that's spinning, going around the unit circle. Now, if I assume all functions are in the form of e to the j omega t, I can pull out the part that I see on the oscilloscope by taking the real part. The real part of e to the j omega t is cosine omega t. That gives you the phasor representation of cosine. In phasors, everything's the complex exponential. The way to represent cosine is 1 times e to the j omega t. So in phasors, 1 represents cosine. If I multiply e to the j omega t times a complex number, do some algebra, the real part, do some algebra, multiply it all out, take the real part, meaning ignore the complex part. The real part has two terms. It's a times cosine minus b times sine. Where the minus sign comes from is j times j is -1, gives you minus b sine omega t. What that means is, in phasors, the complex number a plus jb represents a cosine omega t minus b sine omega t. So this is how you go from sine and cosine to phasors. And that's the beauty of phasors. I can represent both the sine and cosine term with a single complex number. So at this point onward, we'll be dealing with complex numbers. I need that because I have two degrees of freedom with a sine wave. I've got a sine and cosine part. That's the real and complex part. Now, in complex numbers, there's rectangular and polar. The polar form, what that represents is a cosine wave. R is the amplitude, and theta is the phase shift. Kind of figure if theta equals 0 degrees, I have a cosine. If theta is 90 degrees, I have cosine omega t plus 90, which is minus sine. So either form is valid. Personally, what I do is calculations, I like rectangular form. In lab, I prefer polar form. And we'll see why in just a sec. So for example, suppose I have a sine wave that looks like this. Represent it in terms of phasors. Well, there's kind of two ways to represent it. I can represent this as a times cosine omega t plus b times sine. That's one way. So in this waveform, there's a cosine term and a sine term. For me, that's hard to see. A second way to represent it is r cosine omega t with a phase shift. This is actually easier to see. In phasor notation, I'd represent that as r angle theta. This is easy to see. R is the amplitude, and pretty clearly, the peak is 5. So I know that r is 5. Theta is the delay. For a cosine, if theta is 0 degrees, the peak would be at t equals 0. It's not. It's delayed by 1 millisecond. So there's the delay. The delay is 1 millisecond. The period is 6.28 milliseconds. That's the phase shift. And if I want to do it in degrees, that's one cycle. One cycle is 360 degrees. And a delay is a negative phase shift. So it gives me 5 at minus 57 degrees. So that's the phasor representation for this voltage. And notice that polar form is kind of what you get in lab. I can see that the polar form on the oscilloscope. The peak is the voltage, the delay is the angle. Now from complex numbers, this also has a real and complex part, rectangular form. That'll tell you cosine and sine. This is, to me, is easier to see. The frequency comes from the period. The period is 6.28 milliseconds. Frequency is 1 over period. That gives you hertz. Omega is 2 pi f. So the frequency is 1,000 radians per second. And then here's the angle is the delay. The peak is the amplitude. So here's x of t. In phasor form, I'd represent that as 5 at minus 57 degrees. If you like rectangular form, take the real part, complex part. That's also the real part's cosine, 2.7 cosine 1,000t. And minus j is sine. A lot of times students forget that minus sign. Minus j is sine, not plus j. So either answer is correct. In phasor form, that's the phasor representation. I could do rectangular or polar. What I'm going to be doing is representing the variables. Capital means phasor form, lowercase means time form. And you go back and forth between the two. The phasor form just pulls out the amplitudes. The cosine 1,000t, sine 1,000t is assumed. Whatever frequency the input is, that'll be the frequency of the output. Okay, so that's phasor representation for voltages. That's pretty straightforward. Just take the peak and the delay in rectangular form, cosine and sine in rectangular form. Okay, so much for voltages. Same thing holds for current. For impedances, if I add inductors, capacitors, I want to represent those in phasors. Now, inductors and capacitors and resistors are all different. The impedance of a resistor is just R. Where that comes from is V equals IR. Anything multiplied by I gives you the impedance. Well, whatever multiplied by I to give you V gives you impedance. So the impedance of a resistor is just R. If I look at inductors, the VI characteristic for an inductor is V is L di dt. Assuming everything's e to the j omega t, that's the basic assumption for phasors. Then I would take the derivative, I get j omega, e to the j omega t. So again, this is I. So the voltage is j omega L times I. Whatever multiplied by I is the impedance, so that's the impedance of an inductor. It's a complex number, which is your phase shift, your differentiator, times omega times L. As frequency goes up, the impedance goes up. For capacitors, capacitors are integrators. The voltage is 1 over c integral of I dt. If I assume I is e to the j omega t, again, basic assumption for all phasor analysis, when I integrate e to the j omega t, I get 1 over j omega times c, e to the j omega t, or 1 over j omega c times I. So that's the impedance of a capacitor, 1 over j omega c. 1 over j is minus j. Multiply top and bottom by j. I get minus j times 1 over omega c. So capacitors have an impedance of minus j over omega c, or 1 over j omega c. Inductors and capacitors are different. Inductors are plus j, capacitors are minus j. Resistors are just R. And also notice the impedance changes with frequency. For inductors, the impedance goes up with frequency. For capacitors, the impedance goes down with frequency. That'll be useful later on when we design filters. That's the circuit where the gain changes with frequency. Now, to remember which is which, inductors and capacitors are different. There's a saying, Eli the Iceman, that says for inductors, voltage leads current. For capacitors, current leads voltage. So for example, if I have a circuit like this, I plot the voltage V1 and the current I1. Voltage comes before current, voltage leads current, that's Eli. That is an inductive load. If I have a capacitive load, plot the voltage and current, you get ICE. Current comes before voltage for capacitors. So if I look on the oscilloscope, I can tell you inductive or capacitor by looking at the voltage and current. If the current comes first, it's a capacitive load. If the voltage comes first, it's an inductive load. So kind of a summary for phasors. If I have a circuit, I can represent it with phasors. Voltages and currents just become a complex number. In rectangular form, The real part is cosine, minus j is sine. Resistors become just R, no change. Inductors become 1 over j omega, inductors become j omega L, and capacitors become 1 over j omega C. So how does that help? Well, suppose I have a circuit and I want to analyze it. I'll switch over to phasors. What I can do is, once I go into phasor notation, I've got complex numbers for voltages, resistors, inductors, capacitors. So everything we did at DC still applies for RLC circuits, except that now I'm using complex numbers. For resistor circuits, resistors add in series. In parallel, resistors add as 1 over the impedances summed, sum of the admittances inverted. Same thing holds for RLC circuits. In RLC circuits, the impedances add. In parallel, they add as the sum of the inverses inverted. So everything we did at DC still applies for AC. For example, here's the circuit. What is the impedance looking in? Well, that's going to be these two in series. This is 300 minus 100J. Those add. These add in parallel, in series, parallel, series. Just like we did at DC, series and parallel still works, only now using complex numbers. So here's one way to do it. I've got the circuit. I'll add these two in series. That gives you 300 minus J100. In parallel with 200, so that'll be 1 over 200 plus 1 over 300 minus J100. Take that sum, take the inverse, you get a complex number. That goes in series with 200, gives you this number. In parallel with J300, to do that, I do the sum of the inverses. So 1 over J300 plus 1 over 323 minus J15. Take the sum, take the inverse, and what you get is 156 plus J161 in series with 100. So all this together looks like an impedance of 256 ohms plus J161. Now that was probably kind of confusing for you. So let's see how to do that in MATLAB. Let's see how to do that on your calculator. In MATLAB handles complex numbers just fine. I would just say, call this Z2. Well, Z1 is pretty obvious, 300 minus J100. Z2 is 200, 1 over 200, plus 1 over 300 minus J100 gives you Z2. Z1 is Z2 plus 200. Right here. Z1 then is the parallel impedance of 300 in parallel with that. So it's 1 over J300 plus 1 over 200 plus Z2. The impedance looking in is Z1 plus 100. Same answer. So I can do this in MATLAB just fine. Now this is a typical test question you're going to get. When you get to a test, you need a calculator that can handle complex numbers. MATLAB works. If you don't have access to MATLAB on the test, you need a hand calculator that can do complex numbers. That's the HP42. This is just a breeze. Works really, really well in circuits. Basically, HP is a company of electrical computer engineers, and they build really good calculators for electrical computer engineers. This is the HP42. It's no longer in production, but it's a free app on your cell phone. So to input a complex number, I would do the complex. So there's rectangular and polar. We go modes, rectangular. I can say 2, enter 3, complex. If I want to do it in polar form, I would do modes, polar, 5 at 27 degrees. And I can switch between the two just by going rectangular, polar, polar, rectangular. Here I'm going to do rectangular mode. I've got 300 minus J100. So that's 300, enter, 100, negative, complex. There's 300 minus J100 in parallel with 200. So take the inverse, take 200, inverse, add inverse. This is 123 minus J15 ohms. in series with 200, in series it adds, in parallel with J300. So take the inverse, take 0, enter 300, complex, there's J300. Take the inverse, add inverse, add 100, done. Piece of cake on an HP. TIs really struggle with this. When you get to the test, in Circuits 1 and Circuits 2 and electronics, pretty much from now on, you need a calculator that can do complex numbers. I like the HP42. It's a free app on your cell phone. You can get similar ones. Shortly, there will be a thing called the Bison 42, a version that you can build with a lab kit, just so you can use it on tests. For my classes, go ahead and use your cell phone. This is a really good app. It's free. Use it. In Circuit Lab, I can also check my answer. In Circuit Lab, what I'll do is I'll build the circuit. I'll build the circuit. In Circuit Lab, you don't have, let's go back, minus J100, J300 components. I have capacitors. This is 1 over J omega C. This is an inductor, J omega L. So what I have to do is just pick omega. Doesn't matter what frequency you pick. Once I pick omega, solve for L, make the combination 300, make this 100. So but let omega be 1 radian per second. Then this is the inductor, 300 henries. This is the capacitor, 1 over J omega C is 100. That's 10 millifarads. Apply a sine wave at the input. Look at the current versus voltage relationship. If I do that, here's what it looks like. Here is the voltage. Here's the current. And remember Eli the Iceman? That's ELI. Here voltage comes before current, so this is an inductive load. The phase shift is positive. The voltage I can pull off in phasor form. This is the peak. The input is 1 volt. Where's t equals 0? Okay, let's just arbitrarily call this t equals 0. The phase is 0 degrees. The current, here's the peak. There, that tells you the current in polar form. Here's the delay. The delay is about 32 degrees. Here's 1 cycle. It's that percentage of 1 cycle, about 32 degrees. The impedance is voltage over current. So let's take that ratio, 1 at 0 degrees divided by, what is that? About 3.3 milliamps at minus 23 degrees, 32 degrees, milliamps. Take the ratio, I get 303 ohms at 32 degrees. Same thing I calculated. So this is how you find it experimentally. Apply sine wave in, measure the output, input, measure the output, take the ratio, well, correction. Take the voltage, measure the current, take the ratio, that's the impedance. That's how you experimentally find the impedance of the circuit. Here's another problem for you. Find the impedance of this circuit. So let's pause the video and let's try to calculate that. Then we'll do that with MATLAB and then with an HP42. So carrying on, here's what you're doing. I first figure out what's in series and parallel. These are in series, that's 10 minus J60. In parallel with J50, gives you that number. We'll talk about that a little bit more in a sec. In series with 40, in parallel with 30 minus J20. When I'm done, there's the answer. So let's do that in MATLAB. In MATLAB, I would say 10 minus J60, call that Z1. in parallel with J50, so 1 over Z1 plus 1 over J50, that's Z2, in series with 40, in parallel with 30 minus J20, gives you same answer. Let's repeat with an HB42. So here what I would do, I would take 10 minus J60, 10 enter negative 60, complex, in parallel with J50, inverse, 0 enter 50, complex, inverse, add, inverse, in series with 40, in parallel, so I take the inverse, 30 minus J20, 30 enter 20, complex, take that inverse, add, inverse. There's the answer, 31 minus J14. Same thing. You see, HPs are just a breeze. I could do that in Circuit Lab. In Circuit Lab, let's apply a test voltage, make that a sine wave. Measure the current. Ratio of voltage over current gives you impedance. Now for these guys, again in Circuit Lab, I don't have J50, so this is actually J omega L. Let's let omega be 1, just because 1's a nice number. Then this is 50 henries, 1/60th of a farad, 1/20th of a farad. And if I build that in Circuit Lab, do a time domain simulation, this is 1 radian per second, 0.159 hertz. Measure the voltage, measure the current. Here's what it looks like. Here's voltage, here's current. Let's let this be time 0. That means that the voltage is 1 at 0 degrees. The current, again, remember Eli the Iceman? This is current comes before voltage. This is capacitive. That is a negative phase shift. The peak, hard to see, it's about 28 milliamps. This is about a minus 25 degrees, actually plus 25 degrees phase shift comes first. So the voltage divided by current is 1 volt at 0 degrees divided by the current, it's about 28 milliamps, 0.028 at 25 degrees, gives you 34 at minus 25 degrees. Same answer. So kind of in summary, real numbers work really well with DC. Complex numbers work really well when analyzing AC circuits. Everything that we did at DC now applies to AC circuits, only now you wind up using complex numbers. And with AC analysis, that's called phasor analysis. That's changing the problem, describing voltages and current sources as a complex number, describing inductors, capacitors, resistors as complex numbers. For voltages in rectangular form, the real part represents the cosine term, the complex part represents the minus sine term. For impedances, resistors are just R, inductors are plus j omega L, capacitors are 1 over j omega C, or minus jx. Again, inductors and capacitors are different. Inductors have an impedance of plus j, capacitors are minus j. Once I represent a circuit using complex numbers or phasors, I can now analyze just like we did at DC. Only difference is I can't really use the DC analysis. I need to get an image out. I want to see a waveform. I want to see the peak. I want to see the delay. I want to see the time shift. For that, I have to do a time domain simulation, or in lab, this is where oscilloscopes come into play. Up until now, we've been using multimeters in lab. For DC analysis, I just need a number. It's 2.7 volts. For AC analysis, I need more information. That's an oscilloscope. For AC and oscilloscopes, I can sit there and look at the waveform. That's what oscilloscopes do. They give you a picture of what the waveform looks like versus time. So that, in a nutshell, is phasor analysis. From this point onward, we'll be using phasors in Circuits 1. And you'll probably be using phasors for the rest of your career at NDSU. That is lecture number 23 for ECE 211, Phasors.